Hey folks, this next stop in 4.2 is about the center of mass, and specifically the velocity of the center of mass. This video can be thought of as a little of an aside before we get to the big part, but it's really important to see what happens to the center of mass when we're considering momentum. We haven't talked about it in a while because when we talk about Newton's second law, we're really describing the entire motion of the center of mass every time we use Newton's second law. It's really in the momentum unit and the rotation unit where we start to see kind of the extensions of that. So to review, we have an equation for the position of an object center of mass. So if we have a heavy object and a lighter object that are separated by some distance, then the center of mass is going to be nearer the heavier object. So this is a mass of 2m, this has a mass of m. The location of the center of mass is going to be closer to the heavier object. Now, a center of mass can be moving as long as one of the objects in the center in the system is moving. So the center of mass describes an object or a system. If any of the objects within a system are moving, then the center of mass might also be moving. Basically, if we took this equation and thought of this as displacement instead of position, and then divided it by time, we would have an expression for velocity. And the way that would look, if I followed the format of the initial equation, I would have the sum of the mass times the velocity of every object divided by the total mass of the system. And once I put that velocity in there, something shows up. Mass times velocity is momentum. So the velocity of the center of mass of a system is equal to the sum of the momenta, so all of the individual momentum values added up, divided by the total mass. And that equation is also in your equation sheet. So the two center of mass equations that you need are available. Okay, so first I want to show you like what that looks like, and then I want to give you the kind of tagline for this video. If I have two carts, sorry I didn't draw this, I didn't actually plan this video out as well as I intended. This cart is going to have a mass of 4 kilograms. It's going to be moving to the right with a speed of 2 meters per second. And then way over here, I have a cart that has a mass of 2 kilograms, and it's moving to the left with a speed of 6 meters per second. And so we're going to use this equation to find the velocity of the center of mass because we don't actually know how far apart these two objects are. So the velocity of the, oops, I didn't need to do that. The velocity of the center of mass is the sum of the momenta of each object divided by the total mass. So the momentum of the object on the left is going to be 4 times positive 2 because it's moving to the right. The momentum of the object on the right is going to be 2 times negative 6 because this object's moving to the left. And then I would divide that by total mass, which is 6 kilograms. 4 times 2, positive 2 is positive 8. 2 times negative 6 is negative 12. I'm going to divide that by 6. That's negative 4 over 6. That's negative 2/3 meters per second, or negative 0.6 repeating. Now, I can apply both of my equations here if I wanted to, but this object over on the left is heavier, so the center of mass is going to be left of the exact center between them, and it's going to be moving to the left based on what we found. And so that is just because the object on the right has a greater magnitude of momentum, and so the overall momentum of the system is to the left. Now, we don't do too much application of this, but it comes with a very important understanding that because the velocity of the center of mass depends on the total momentum of the system, we have a special case here. If the net force on a system is 0, then the total momentum of that system is constant. So there's nothing that's going to change the momentum of the system. Therefore, the speed of the center of mass is constant under all situations involving conservation of linear momentum. And that's kind of a weird idea. And we can apply it. I'll do a demonstration of this in class. But we can apply it to this situation here. That when these two carts hit, they are actually going to hit at their center of mass, which is moving to the left. When they hit each other, they will exert a force on one another. But if I think of these two carts as one system, then the system's net force will be zero before, during, and after that collision. So the net force in the system when they collide is zero. That means the total momentum of the system is constant, and therefore the velocity of the center of mass will stay the same throughout their interaction. Whether they stick together or bounce off one another, the center of mass will continue moving at negative 2/3 meters per second the entire time. So that's kind of a weird thing. So like remember this. It doesn't come up very often, but when you have a system of objects, the velocity of their center of mass will stay the same if they collide.